we finish looking at firms' decision making for production in the short run, we can turn to their decision making in the long run. Remember, in the long run, a firm has enough time to change all of its inputs. So not just short-term things like labor that we can quickly change, but much more longer-term things like capital equipment or the actual facilities that they're renting. So in the long run, the production process is described, and what we want to think about is returns to scale. So returns to how large the firm is actually getting. So return to scale can be thought of as the resulting increase in total output as all inputs increase. Remember, in the short run, we're trying to use as many variable inputs as possible to maximize our returns, given that we're subject to this constraint that we only have those fixed resources. We can't increase them at all. So it's trying to find the most we can with the variable inputs. Now we're trying to figure out where we should produce at, how many resources we should use when we have all the inputs at our disposal. We can make any decision we want. Now you might think, like off the top of your head, if you're going to increase the size, say you double the size of all your resources that you're putting into production, so all your inputs, that you would automatically just double your output. But that might not be the case. So if you double it, output can more than double. That's called increasing returns to scale. So if you double all the resources you're putting in, all of your inputs, you end up with more than that. It could exactly double. We call this constant returns to scale. And it can less than double. We call this decreasing returns to scale. So if you double all the inputs you use, you end up getting less than double back. So why is this the case? Why can we see different returns to scale? So for one thing, a larger scale production, so a larger company, might enable a firm to divide tasks into more specialized activities. We talk about the division of labor allows people to specialize at certain tasks, and they get really productive. If you focus on one thing all day, you end up getting really good. We saw this very early on in the history of like factory management, where instead of having one person do all 100 tasks it takes to make a pin, have them all focus on like 2 or 3. They became incredibly more productive because all they did was that one little thing all day and quickly moved on to the next. They might also be able to afford, because they're that much larger, better and more productive capital equipment. Which again, that should increase their returns to scale more than just, doubling if they double the amount of inputs. In other cases, operating at a larger scale might create inefficiencies. So this could be like managerial inefficiencies. There's communication problems. There's a lot of bureaucracy that won't let you make decisions. Like when IBM needed like 50 different VPs to sign off on any slight change to a product. So this can cause decreasing returns to scale, that even though you're getting so much larger, there's so much more to manage, there's so much more going on, you end up with bloat, you end up with waste, and you end up with communication difficulty that just slows things down too much. So one way that we can measure the returns to scale is to use a coefficient of output elasticity. And this is going to be just like our simple elasticity equation. So the elasticity of the quantity produced equals the percentage change in Q divided by the percentage change in all inputs. Again, this is a long term, so we're considering all inputs. So if the elasticity is greater than 1, then we have increasing returns to scale. If elasticity equals 1, then we have those constant returns to scale. So if you double the inputs, you get double the change in quantity. And if elasticity is less than 1, then we end up with decreasing returns to scale. So if you double it, you're getting less than double back. Let's return to the equation we described at the beginning of the chapter, where Q, and the quantity being produced, is a function of 2 inputs, X and Y. Well, for example, let's say we increase the production by 10%. So if we increase production by 10%, or the inputs by 10%, the K variable here in front of the X and the Y, those will increase by 10%. So we'll multiply that by 1.1%. If we do that, Q is going to increase by some amount. We can represent that by H. So we end up with H times Q equals a function of K times X and K times Y. If H is greater than K, so if the increase in Q, in the total quantity output, is greater than K, the increase in the inputs we're putting in, then we have increasing returns to scale, or the elasticity is greater than 1. If H equals K, so that 10% increase in the inputs yields a 10% increase in the total quantity being produced, or total output, then we have a constant returns to scale. And if that H is less than K, so the change in the output is less than the change in the input, then we have decreasing returns to scale. And remember, our elasticity of the quantity is less than 1. Like most things we cover, I think it can be seen better if we show these graphically. So for increasing returns to scale, we have on the left-hand side, we have the total quantity being produced. And on the right-hand side of that graph, we have X and Y. We have our total inputs being used. When a firm has increasing returns to scale, the increase in the quantity is going to be greater than the increase in X and Y being put in. So we're going to have a really steep graph. For constant returns to scale, as we increase Q, we increase X and Y by the same percentage. So we're going to have a straight line at a 45-degree angle. We have a 1-for-1 change in each. And for decreasing returns to scale, we're going to have a greater increase in X and Y in those inputs than we will in the output Q. So it's going to be a more shallow slope like we see there. Early in the chapter, we established a short-run production function. So the short run, remember, is characterized by having a fixed factor, and then you have variable factors. One of the inputs is fixed. So we represented that by the equation Q equals F, or a function of labor with a subscript capital. The subscript capital K shows us that capital is fixed, that's our fixed input that's never going to change. So the quantity we produce is only a function of how much labor we add. So as we moved later in the chapter, and as we started to get into this production in the long run, we assume the production function starts with increasing marginal returns, followed by decreasing marginal returns. That's what we saw when we were trying to determine where to produce. So that situation, that type of curve is represented by a cubic function. So, for instance, we can have Q, the quantity produced, equals A plus, so a constant, plus B times L plus C times L squared minus D times L to the third power. So basically just a cubic function where the quantity produced is a function of labor. We could also have a quadratic function. Sometimes there's no stage 1 where we have those increasing marginal returns. And in that case, we'll have a quadratic function. So something like Q equals A, the constant, plus B times labor plus or minus C times labor squared. We can also represent the production function using what's called a power function. A power function is when you have an exponential for one of the inputs. So let's imagine a simple one where Q, the quantity being produced, equals A, the coefficient, times L, our labor variable, to the B power. So now the direction of the marginal product is going to depend on the size of the exponent, that B variable. So if B is greater than 1, then the marginal product is increasing. If B equals 1, it's going to be constant. At that point, you just have L to the 1 power equals L. And if the B variable is less than 1, it's going to be decreasing. So if you have B equals 2, then you end up with the labor squared. So an advantage of this is that it can be transformed into a linear equation, so like a regression equation, when you express it in long terms. So if you divide everything by logarithm. So an example of a production function that's been used for almost a century now is the Cobb-Douglas production function. So they use an exponential equation, and there are two variables, L, labor, and K, capital. They estimated this in 1928 for manufacturing output in the United States between 1889 and 1922. It's been in use ever since. So the basic equation is Q equals A, so some variable, times L, labor, to the B power, times K, capital, to the C power. Because we're going to have numbers for L and K, we would fill it in this model, and we multiply those together. If we add together B and C, those exponents, and they're greater than 1, we'll end up with increasing returns to scale. If we add B and C together and they equal 1, we'll have constant returns to scale. And if we add B and C together and we get less than 1, we'll experience decreasing returns to scale. George Stigler joked that it's the common practice in economics when you're doing price theory to deny the validity of the Cobb-Douglas function because it's too simple, and then use it as what he called an excellent approximation. Now, the reason it's endured for so long and it's used so constantly is it has a lot of advantages. So the first is that it can investigate the marginal product for one factor holding others fixed. And again, this is very useful for us because we want to try to simplify. We want to make some assumptions. We want to look at what's the effect of varying one input. Also, the elasticity of factors are equal to their exponents. Basically, this means it's very simple to work with. We see those numbers. We don't have to calculate things out. So when, like on the previous slide, when we're talking about increasing returns to scale or decreasing returns to scale based on adding those variables or adding the exponents B and C, because the elasticity are equal to their exponents, we just add those together. Very simple to calculate and to work with. It can be estimated by linear regression. So if we take the natural log of both sides of the equation, we end up with the natural log of Q, and then we have no exponents on the other side. So very simple to do the math out for that. It can accommodate any number of independent variables, so we can make it more complex if we have to. And it does not require constant technology. So it incorporates the fact that capital can improve over time. Obviously, in 1928, we didn't have computers. Now we have computers. But we can still work with the Cobb-Douglas production function if we have a massive change in technology like that. Now, it does suffer from some shortcomings, as all models suffer from shortcomings. So the first is that it can't show marginal product going through all 3 stages in one specification. So when we had that cubic function that approximated the graph we had early on showing all 3 stages, we can't do that with a Cobb-Douglas. Cobb-Douglas also can't show a firm or an industry going through the increasing constant and decreasing returns to scale. Again, you need a cubic function to do that. There are also important problems with the specification of data that is used in empirical estimates. We're not going to get into too much detail with that, but it is something that we should talk about. When we try to do a statistical estimation of production functions, there are some difficulties with the data that we need to keep in mind. So first of all, inputs should be measured in flow rather than stock variables, which isn't always possible. So flow variables measures the actual usage of services that are consumed while producing a product. Stock variables are the amount of factors present. So for example, labor, which is usually the most important input, our stock is going to be the number of workers. Now again, you might not use all those workers, and they might not use them entirely in production process. So you would want a flow variable like number of hours worked. And the most difficult input variable to try to measure is capital. Another thing just in general for these variables is you want to have the same figure for each of them, whatever that is. So for labor, it's fairly simple. We can have the total hours worked. Most firms keep track of that. But for capital, that's much more difficult. So we have the plant, we have machinery in there, we have equipment that's being used in production. All these different components, we need to compute them into some common form, or one single variable. And that can be very difficult. And then we have to choose between time series and cross-section analysis. So with time series, there's some problems. You have to make adjustments for inflation in that period. You have to account for depreciation. You also probably should include a time variable or some kind of dummy variable to account for changes in technology over time. If you do cross-section analysis, on the other hand, you can have some problems. Again, you're going to have one time period, but a lot of different firms or a lot of different plant locations. If you do that, different plants might not use the same level of technology. Some might have brand new equipment, some might be working on older stuff. And so there's differences there you need to somehow try to reconcile. And if there's data in monetary terms, you have to adjust for differences in prices or wage levels or even the cost of physical capital in different geographical locations. There's a lot of variation in cost of living and cost of production across just like within the United States, let alone across the world. We can also use the Cobb-Douglas function to estimate aggregate production function. So we could look at entire industries or even an entire economy. So a lot of this work has been fruitful in describing production functions, but the interpretation results may not be as meaningful as we get for individual firms. There can also be difficulty gathering data for aggregate functions. So for an economy, you could use GDP, but is GDP the most effective estimation of the health of an economy? Could you use GNP instead of GDP? There's issues like that to tease out. And for an industry, you can use data from the Census of Manufacturers, Production Index, from the Federal Reserve. For labor, you can use data from the Bureau of Labor Statistics, but then again, trying to make sure that all of those comparisons are apples to apples, that you get them down into one appropriate variable. It can be difficult. Sometimes it's simple, sometimes a lot less simple. If we're working over time, inflation data might not be very good. It may not account for technological changes, and we still have to account for technological changes overall in our production function. If we're looking across economies, doing a cross-section, there can be a lot of differences, not just in the technology being used and the cost of living in all those different countries. You could have cultural issues that affects the labor variable as well. Production functions can be very important in the managerial decision-making process. So remember, careful planning is essential to help a firm use its resources in a rational manner. If they're trying to maximize their profits, you need to engage in careful planning, you need to set targets, you need to gather enough data to understand what's going on. Now, production levels don't depend on how much a company wants to produce. What they depend on is how much the customers want to buy. Oftentimes, firms may find themselves in stage 1 or stage 3. These are suboptimal stages to be in. They want to be in stage 2, remember. But if managers know that, if they know they're suffering from diminishing marginal returns to the point that their marginal revenue is negative, or they know that they're in stage 1, and if they increase the number of workers they hired, they could increase their average production. Why would they do that? Because they're limited by how much consumers want to buy. They're not able to produce enough to be able to move out of stage 1 into stage 2 and actually have their products sold. So you have to have careful planning regarding the amount of fixed inputs that you have in the short run, along with the variable inputs that you hire. If you don't have enough in the short run, you will not be able to reach your target output that you could actually sell to all the customers who want to buy. Likewise, if you had too many, you'll end up with machines sitting idle, half of your factory sitting empty, because people don't want to buy as much as you're able to produce. Now, good capacity planning also requires two basic elements. So the first is accurate forecasts of the consumer demand, and the second is effective communication between production and marketing. And we understand why having accurate forecasts of demand is important, but it's also important to have communication between managers in the different sections of your firm and even some of the people above them making the overall decisions. If you've worked, especially like in some sort of factory or firm that has manufacturing as part of their component of their business, you can know that sometimes the engineers are designing things or production is producing as much as possible, not caring about what's actually being sold or about whether the consumers actually want to buy it or how user-friendly it is even sometimes. That they're in their own world and they're just trying to optimize what they're going through. So their target is, produce, I don't know, 100,000 units. And it's like good if you make more, they may try to hit over 100,000 units, regardless of how many the sales staff can actually sell. Now, the intensity of global competition that has increased substantially over the past 40, 50 years requires managers sometimes to go beyond these simple production curves. They have to consider more stuff. For instance, one thing in order to be competitive in the modern marketplace is managers understanding the importance of speed and flexibility. They call this lean manufacturing, often using just-in-time inventory. So instead of having a lot of stuff sitting around, you have very little waste. You're not producing too much, but you're also not waiting for um, waiting for the next set of inputs to come in. You don't have a lot of inputs sitting around wasting space. You're not, you don't have a ton of inventory waiting to be shipped out. Everything is trying to be optimized so you have as little waiting and as little waste as possible. We did see why some redundancy is necessary during the supply chain crisis, during COVID, and what's still going on now. So firms have had to make a decision: how resilient do they want to be? How much do they want to be able to withstand quick fluctuations or short-term fluctuations versus how much they want to just optimize their production process, lowering their costs as much as possible and not wasting.